One of the most powerful features in Etabs is the Auto Line Constraint option for floor and wall objects. This feature frees the user from the complicated and time-consuming task of creating a transition zone mesh between objects of different sizes and orientations. In this example, we will look at how line constraints work with walls. Here we have two different views of the same wall. On the left is the object model that the user has created, and on the right is the internal mesh. In a traditional finite element model, this mesh would cause problems due to the fact that the joints of one element are not connected to joints at the adjacent element, resulting in a discontinuity. In fact, in this model, the only place where the joints align themselves is at the story levels. However, with Etabs, the Auto Line Constraint option, found under the Assign Shell Area command, automatically defaults to constraining these unconnected joints to the line edges of the adjacent elements, thereby eliminating the need to create a transition mesh. Now let's see how this works. We will run an analysis containing a lateral static load case. And on the plotted deformed shape, we can see that the analysis model has maintained continuity even where the mesh is not in alignment. This result is also echoed in the display of the wall stresses. Next, we will unlock the model so that we may change the Auto Line Constraint assignment. For this analysis, we will remove the line constraints. To change the assignment, start by selecting a wall object and go to the Assign Shell Area Auto Line Constraints command. Click on the Do Not Create Line Constraints option and make sure that the Apply to Full Structure is checked. We can now rerun the analysis. The deformed shape now shows how the spandrel beams, without their ends constrained, can move almost independently of the adjacent walls. In fact, the walls appear almost to be uncoupled because of the lack of continuity at the spandrel beams. Thus, for the walls, the Auto Line Constraint option is extremely beneficial for capturing the proper behavior. Now let's take a look at how the Auto Line Constraint option works for slabs. Here we have two different slab models to represent the same physical slab, namely a single slab supported by 6 columns. The top model has 2 floor objects, with the object edges offset from the grid line B. The bottom model also has 2 floor objects, but the object edges occur centered on the grid line. The meshes also differ between the two models. The top model uses 2 different meshes that do not align, while the bottom model has 1 consistent mesh. In a traditional finite element program, the 2 meshes of the top model would be connected only at the outside corners. Now let's run the analysis. And take a look at the slab forces. Although the 2 force plots are not identical, they are reasonably close, which shows that even with variations in meshing, the Auto Line Constraint option does a good job of capturing the appropriate behavior. Next, we will remove the Auto Line Constraint. Start by unlocking the model and select both slab objects of the top model. Go to the Assign Shell Area Auto Line Constraint command and select the Do Not Create Line Constraints option, and make sure to uncheck the Apply to Full Structure box, as we only wish to change the constraints on the top model. rerun the analysis, and display the slab forces. Notice how drastically different the distribution of forces is now that the line constraints have been removed. This would be the default results obtained with a typical finite element program. We have looked at how autoline constraints work with walls and slabs individually, and now we will look at the situation where the model involves both. In a typical finite element program, one of the most difficult modeling tasks occurs at the intersection of walls and slabs, as the meshing of the two objects is almost always different. In this case, the problem is compounded by the fact that the slab is on a diagonal to the wall, which means that only a few slab joints line up with the joints of the wall. However, the autoline constraint option automatically constrains these unconnected slab joints to the line edges of the wall elements, as shown here, thus providing the needed continuity. We will run the analysis, and the display deformation pattern is as we would expect. If we window in, note how the wall and slab are connected and deformed together, with the slab spanning from the wall to the outer frame. Next, we will unlock the model so that we may remove the effects of the autoline constraint option. Select a single area object and go to the Assign Autoline Constraint command. Select the Do Not Create Line Constraints option, but leave the Apply to Full Structure box checked. Now rerun the analysis with the Autoline Constraint option turned off. This analysis results in a deformed shape that is completely inappropriate due to the fact that the slab is connected to the wall at only a few points. Thus, the default autoline constraint option of Etabs, which constrains free joints of elements to adjacent element edges, eliminates the difficult task of creating transition meshes as required in typical finite element programs. This concludes this tutorial.